Welcome to the session called Electroacoustic Software Solution, Development with the new HBK Electroacoustic Engine software. Internally, we call it the EA Engine, and we've been working on that new software platform for quite some time, so I'm very happy to talk to you about it today. My name is Vince Ray. I joined HBK in 2013 and became a key account manager for the company. I live in Santa Cruz, California, close to the Silicon Valley and San Francisco. Today's presentation is for all customers who would like to develop their own electroacoustic apps. So I don't want to waste any time. Let's move on to the presentation. Hottinger Brilliant Care has a long history in electroacoustic testing, and I still meet engineers who own and use the famous BNK 2012 analyzer. But I must say, the new generation of engineers I meet today have a lot of different skills. One of them is their coding knowledge, which makes a big difference between now and then. Another consideration is a lot of engineers have used Pro Audio sound cards to test electroacoustic devices. These Pro Audio sound cards are fairly inexpensive, well designed, they can easily use and mixed analog and digital stream, but they require external signal conditioner, power supply and cables to interface with measurement grade transducers. And usually comes with a very complicated mixing table software that is difficult to configure. At HBK, we believe in simpler design. Here's our solution. HBK introduced a few years ago the 3670 audio interface. It has 8 inputs, 2 outputs, has a sampling frequency of 96 kHz, 24 bits. It has no buttons, no fans, and I would say no problems. That could be another song here. It has CCLD signal conditioning, so you can connect microphones, accelerometers, force transducer directly to the box. It has a USB interface, low noise floor, an ASIO driver, and the team in Europe worked very hard to have a fixed latency between the input and the output on this device. Let me explain what we mean by latencies. If you connect the input 1 to the output 1 of the 3670 with a BNC to BNC cable, and if you generate a sine wave, for example, you will notice a time delay between the two. This is called the electronic latency. It is not due to the cable length like I heard before, but rather due to the firmware and driver processing time. The 3670 belongs to a class of electroacoustic interfaces that have fixed electronic latency. So for each measurement, we know the exact number of digital samples, which will stay the same, between the input and the output. So we can compensate for it once the data is generated and captured. Wait, there's another latency we have to take into account, which is the physical latency between transducers. In my case here, it's a microphone and an artificial mouth. And due to the distance between the two transducers, we have that physical latency that will impact the synchronization between the input and the output again. Well, we can use some kind of cross-correlation technique to estimate the time delay between the input and the output and then compensate for it. So let's imagine now that you're developing a quality control test station where you have fixed microphones and speaker locations like the one on the screen. By definition, in that case, the physical latency will be identical for all measurements. And if you use a 3670, the electronic latency is fixed. So you can measure the total latency once and never have to calculate it again. You will save a lot of precious processing time. We believe the 3670 is a great hardware platform for connecting measurement grade input and output transducer. But what's next? Well, we're going to talk about software now. The EA Engine relies on 4 principles, and I must say, most of the time when I met engineers, they would interrupt my presentation after a couple of minutes and would say something like, "Thanks, Vince. I'm sure what you're going to show us is fine, but truly, what is your API? How can I connect my code to your audio interface?" So what the electroacoustic engine will do is to simplify the access of the 3670 ASIO digital streams. The second principle is calibrated DSP. And what do I mean by that? We're well aware that DSP tools are available everywhere, and you can process an FFT with even Excel, for example. But what you get is a raw complex spectrum, and what you need is typically magnitude and phase. It is rather simple to transform a complex data set into magnitude and phase, but typically to get an FFT without leakage, you need to pre-process the time block with a special window like Hanning or Hamming before you do the FFT, and that will affect the magnitude of your spectrum. So when you use an FFT processing function, you need to make sure you don't have any leakage, and your code will provide a corrected magnitude. This is what the electroacoustic engine will do for you, and this is what I mean by calibrated DSP. The third principle is no graphical user interface. This is a common request where test engineers want to use their own graphic tools to plot data. Or when you develop a quality control application, you even don't need any graphical representation, but rather a pass-fail metric. So that makes the electroacoustic engine a true toolbox. Finally, to close the loop, the fourth principle is simple API. The HBK electroacoustic engine works on Windows. It can communicate with the 3670 and has different modules. An I/O calibration, where it can calibrate an input channel or an output channel. It can equalize. It can do random test, swap sign, step sign, waveform streaming, so you can play a calibrated wave like speech or background noise. And it can do a time recording. Additionally, it can do frequency analysis, so we support spectra, phasor sign, frequency response function, nth octave analysis. It can do THD and rub and buzz, and we'll add more down the road. Because the EA engine is a toolbox, it doesn't have any graphical user interface. So you can have your own user-defined test control that you can program yourself and interact with the engine via command lines. If you want to go in a detailed configuration, we have a set of config files that you can read or write to adjust the test the way you want. And the EA engine will output test result as XML, CSV, WAV files, and MATLAB. Additionally, if you're working on speech quality, feel free to add a Pascal Piolka algorithm to your own app, or electrical impedance, or turntable control, pass-fail metric, and we believe people will create great things we haven't think of yet. And this user-defined test control can be done in MATLAB, Python, Visual Studio, or any other application that would support command lines and read and write XML files. All right, let me show you a very simple example where I want to calibrate one of my microphones, and I'm going to call this test input calibration test, right? The microphone is connected on the input 4 of the 3670, and the microphone is connected to a calibrator. And I want to make sure that the reference frequency is 1000 Hertz. I'm using 1 Pascal RMS, and the duration for calibrating the mic is about 5 seconds. Okay, so in order to modify those parameters, I need to open the config file that relates to the calibration. All right, the file is just right there. So you can see that the reference frequency is 1000 Hertz. The reference level is 1 Pascal RMS. My calibration duration is 3 seconds. I want to modify that. I want to make 5 seconds. And I want to make sure that the results are exported as an XML file. You can see that we can calculate THD using the calibrator as a source. So you can check the THD of the calibrator if you like. And I have a section here called Analysis FFT Setting, which is basically my FFT analysis. So you can specify a number of lines. We're using a flat top window here for that test. So the exported results are going to be the spectrum and the sensitivity. The sensitivity will go to a config file associated with the input channel, and the FFT will go to the result file. All right, let me show you the command line now. So I'm going to use the Windows command prompt. It's going to be simple enough, and the Windows is just right there. And I'm going to type in EA Engine calibrate input channel 4 and return key. After the 5 seconds, The engine will calculate everything for me. So I can read directly here on the prompt that I have a sensitivity of 10.93 millivolt per Pascal. That sensitivity is now in an XML file, and my test results now includes my FFT analysis. You can see that here. If I double click it, so I can see my auto spectra, I can see my frequencies, I can see the amplitude of the auto spectrum. So we can see that we're exporting Pascal RMS, so it's a power value. And then I've got all the information regarding the THD as well. I would like to give you now a more substantial demo of the EA engine using this head simulator type 5128. It has a mouth so it can talk, two high frequency artificial ears so it can listen and can measure headphones, for example. My headphone in that case is connected to the output 1 and output 2, and the ears are connected to the input 1 and 2 of the 3670. So this is a simple 2-in, 2-out test. Here's the GUI I put together in Visual Studio that allows me to configure a very quick test. So this GUI has multiple components. So I've got a data grid here where I can quickly activate, deactivate a channel if I want. So every time I click a checkbox here, I'm adding a graph to the display here, but also I'm pushing the information to the config file that EA Engine will read later. So if I check this box here, the EA Engine will know that input 3 is activated. I have a Vmax column where I have voltage information regarding the 3670, and this is the voltage before clipping. I've got a latency test, so I can estimate the latency between the input and the output channel, a sensitivity, an engineering unit, and I picked up a couple references for my frequency response function or my phase assigned spectrum. So generator 1 is assigned to input 1 and generator 2 is assigned to input 2. This GUI can do an input calibration, so I'm going to jump on this input calibration test method, and I can select the input channel I want to calibrate. So my calibrator is on input 2 actually, on the right ear of the head simulator. As a calibrator, I define here a B&K 4231 plus DI0658. This is the little accessories which is helping for connecting the ears to the calibrator. So I'm going to pick that one. And you can see the reference level is not 1 Pascal RMS, but 1.15088, so 95.2 dB. It's still 1000 Hertz, and the calibration time, I selected 5 seconds. That's long enough. And I'm going to also estimate the total harmonic distortion using the harmonic 2, 3, 4, and 5. Completed. The new sensitivity is 11.7850 millivolt per Pascal for the right ear. So now I'm going to calibrate the input 1, which is the left ear of the head simulator. All right, so I just have to pick up input 1 here and pick up my 4231 with DI0658, calibrate. All right, so the sensitivity of the left ear is 13.6501 millivolt per Pascal, which is fine. So in that GUI, I have this little tree view here where I have listed all the measurement I've done so far. So the top one here is for my left ear. The bottom right is for the right ear. So you can see the 95.2 dB using this is an FFT using a flat top window. You can see the distortion coming out of the calibrator, but this is normal. The THD is less than 1%, which is fine. This is in spec here. So we're good to go to the next step. While we're calibrating the head simulator, I just want to quickly show you how you can calibrate the artificial mouth as well. I have a 1/4-inch reference microphone on the input 3 of the 3670, which has a nominal sensitivity of 10 millivolt per Pascal. If I read the calibration certificate of that microphone, I know the sensitivity is 10.52 millivolt per Pascal. So I can enter that value, and if I click enter, the GUI will push out a new XML field in the input channel config file that the EA engine will be able to read. And I need to specify an output channel number and a reference input channel number here. So I just connected the mouth to the output 1 of the 3670, so this is correct. But my reference input channel, I want to use my reference microphone number 3 here. And you can see that the output calibration has two sections. There's a section where I'm going to output a cal tone of 1000 Hertz. This is something you can configure yourself. I'm going to output 10 millivolt RMS to the mouth for a duration of 5 seconds. So let's calibrate it. Right, and you can see that the EA engine generated a new sensitivity for the generator 1, which is 25.1638 Pascal per volt. So we're dealing with a speaker here, this is why. And now I'm ready to do the equalization. I can specify a target level for my EQ, a start frequency, a stop frequency, a stimulus. I'm going to use a step sign here with an R80 resolution, 12 cycles for the low frequencies, and 10 milliseconds for the high frequency. You can see that the EA engine generated two result files, which are listed in the tree view here. The first file contains the sound pressure level coming out of the generator. And I asked for 80 dB, and this is exactly what I got. And here's the response measured by the reference microphone. And you can see that at 1000 Hertz, the reference microphones measure 80 dB as expected. The next result file contains the frequency response function that will be used for the equalization. So I can check them all here and expand the view. So the bottom left diagram here shows the FRF magnitude of the equalization. You can see that we're going to boost the low frequencies to compensate for this roll-off here. And then we'll do the same for the high frequencies. All right, so the mouth is fully calibrated and equalized. I just want to move to a different test method here. You can see that we have a time data recording. So the time data recording is a wave recorder. I have activated 3 input channels, and I'm going to record my waveform for 3 seconds here. Okay, so in the tree view I have a new wave files, and I can activate each of the channel just selecting the channel accordingly. The file format we use for wave files is a 32-bit floating numbers. So you don't have to do any calibration. The numbers you have in the wave files are the calibrated Pascal value that we have here on the screen. Good. All right, next one is the step sign. So I still want to capture the frequency response and distortion of those headphones, and I really don't need the input 3 anymore, so I'm going to deactivate it. Next step is to make sure that the FRF have been selected correctly. And the remove latency has been checked. I want to make sure the input and the output are sync. And I want to turn on both generators of the 3670 outputting 100 millivolts from 80 Hertz to 12 kilohertz with a resolution of R80, 12 cycles for the low frequencies, and 10 milliseconds for the high frequencies. The DUT name can be changed here. I'm going to export everything as an XML, and I can save the audio recording if I want to. All right, I want to make it simple for now. We're going to click Start and review the result later. All right, let's see what we have inside the test result. You can see that we have a few auto spectrum here from the generator 1 and 2. I asked for 100 millivolt, and this is what I got. I have also the response at the microphone located inside the ear simulator. So this is left channel, right channel, and here's the response due to the headphone excitation. And I have my FRF. So I've got the magnitude and phase of the FRF, and I can display those. So this is for the left cup, and this is for the right cup. I want to add THD now to the test result. In this GUI, you just have to click this checkbox, and you can see that we're going to do a classic THD according to the IEC standard, and we're going to use the harmonic 2, 3, 4, and actually I'm going to add number 5 here. All right, so the EA engine will know that we're going to use all those harmonics for computing THD. Let's have a look on the new test result, and you can see that we have much more items to discuss here. We still have all the auto spectra from the generators, from the left and right ears, the FRF we computed before, but now we have access to all the harmonics due to the fact that we have enabled THD, and the EA engine will compute THD for all active channels. That includes input and output. So you can imagine on the generator side, by definition, there's not a lot of distortion coming out of the 3670. Let's verify that. So here's the generator 1. Distortion is close to 0. And this is generator 2, close to 0. That is not a surprise. But let's have a look now on the distortion for the left ear. So you can see that we have access to harmonic 1, 2, 3, 4, 5, according to our selection there. And we have also what we call a total distortion. Total distortion is the summation of all the selected harmonic presented at dB/SPL. And then we have a more classic view, which is a THD percentage. So you can check that box. And now everything is presented as a percent, and you can see those headphones do not have a lot of distortion. And we can do the same for the right ear. All right, so this is a fairly quick test where you want to do a frequency response measurement, but you still have access to the auto spectra, and you can quickly display THD if you like to. This GUI is also capable of calculating electrical impedance by just activating those two lines. I can also activate a turntable and tell the GUI what kind of increment I want for my polar plot. At this point of time, the EA engine can support different test methods. So you can do swept sign test, and random test, waveform streaming test. So this is going to be useful for playing back calibrated speech and calibrate background noise. The GUI will integrate a polka metric and some scripts and commands and some other things that will come along. All right, guys, I hope you have a good understanding on the EA engine capabilities. And now I would like to give you a quick tutorial on how to interact with the toolbox from Visual Studio. There are actually a couple of ways of doing so. The first one is to use standard Windows components for sending command, getting feedback, reading and writing XML files. But the team in Europe put together an EA engine library that will help you to send command and getting XML data through functions. This is a little bit more elegant, that will save you coding lines. But if you want to see a good demo of the EA engine library, I recommend watching the presentation at 11 a.m. this morning. I think it's a good time now to show you a simple example in Visual Basic. That's going to be my programming language I'm going to use today. And in that example, we'll build a simple app that will do a couple things. We'll do a calibration check. So I want to calibrate a microphone, get its sensitivity. And what I want also is to do a frequency response measurement with THD. And on top of that, I want to make a pass-fail metric to visualize what my FRF and THD fits in some tolerances curve, right? Okay, so I'm going to start by adding button to the form. I'm going to have a button on top here, which will be my Cal Mic 1 button. So when I click that button, I want to start the calibration process. I'm going to have another button for doing my FRF, that's THD. And I want to have a couple other buttons. One will be dedicated for sending commands. So I'm going to call it send command. And this one will be for stop command. stop command. All right, perfect. I want to move that up here, and you'll see that the EA Engine will provide us a lot of text, you know, so I want to be able to collect that text and plot that in a rich text box so we can read what's going on here. And those rich text boxes are very convenient because we can plot a lot of text. And on top of that, I want a simple text box. So I will put the text box here. It's a little high. So I'm going to move that one here, move that one there, move that text box right there. Okay, perfect. And then finally, I want a status strip, which are nice. And I'll put them at the bottom of the page here, and I'm going to bring a label. Okay, so I'm going to say this label will plot the clock while the engine is running. And finally, I want to have pass-fail labels. I'm going to have a pass-fail for my calibration here. It's going to be label 1. And I want to have a pass-fail for my FRF and my THD. This one will be dedicated for the FRF, and the other one will be dedicated for the THD. Okay, and I'll play with the colors. So know if I pass, I'll turn the label green. If I fail, I'll turn it red. You know, to make it simple. So this is it. This is the GUI I'm going to use here. Fairly simple, but now we have to put some codes behind the buttons and the different objects. Okay, I'm going to add some code now under this send command button, and I'm going to start with a cmd equals new process, and this object basically is my command line mechanism that requires several parameters, and you can notice that I'm going to use the text box 1 that I had on my user interface to send arguments, in other words commands, you know, like for example calibrate channel input 1 is considered as an argument, and I want to raise also events. So there's a couple events I would like to deal with here. The first one is called output data received. So every time the engine sends some text back to the user, I would like to plot it in a text box or in a rich text box. So I'm going to use a function called myDataReceived, and I prepare that function already. So we're going to save a little bit of time here, but basically that function will be triggered every time we will receive text. And if the text starts with time, I want to plot the clock in the status strip object. If I have an issue with a device that is not connected to the computer, I want to be notified, and you can see that I'm using a flag here set to true. You will see why in a second. And for everything else, I want to use the text box. Okay, so the next thing here is the exited event. This is an important event because when the command is completed, I want to make sure that the application gets notified automatically. So I'm going to start a new function. I'm going to say private sub myExit, and once I have that, I want to close the object. So cmd.close first, close, and I will do dispose. There we go. But you know, when the device is the 3670 is not connected to the computer, I want to skip the close and dispose here. So I'm going to use the flag. So I'm going to use a if here, and I'm going to close the if right there. Okay, so when the 3670 is not connected, I want to skip the close and dispose to avoid some issues. All right, so I think we're almost done here. I just need a couple more lines, and the first one is the start. So we want to start the command, and then we want to initiate or initialize the myDataReceived, and I need to start with this beginning output read line, and automatically you know, the text will get populated in the read text box or the status bar. All right, so I think we're good, and I'm going to demonstrate a simple command in the next step here. I'm back to the graphical user interface and I'm going to execute it. And I'm going to start with a very simple command that the engine should be able to understand. Version. You can see that the engine sent me back the version of the software I'm currently using. So this is working pretty good. Another command that the engine should be able to recognize is the get input channel status. And it returns the input number and tells me if it is active or not active. So this one is false. The only active channel is my input one. All right, next I want to work with a stop now. So I'm going to have to bring back the function that I already prepared, and which will save me time. But basically this function will search for the EA Engine application, and if it sees the EA Engine is up and running, it will kill it, right? So it will stop the command, and the engine will handle that very well. All right, so now we have the command line mechanism in place. I'm going to work on the CalMic 1. So first thing I'm going to do is to specify the command to the text box 1, right? So it's going to be calibrate input channel 1. The second thing is going to be write input calibration setting underscore XML. So this is a function that I already prepared. I'm going to show you how it looks like. But basically this is a function that's going to write data in an existing config XML file which is on the drive. And I'm going to force, for example, the frequency. I'm going to force the reference level. It's going to be 1 Pascal here. And I want to calibrate for 5 seconds. And once I have defined those parameters, I want to save the new XML file. Okay. For your information, the XML is sitting right there with other configuration. And we're going to talk about this one here, calibration settings. So if I open that up, that file was installed when I installed the EA Engine previously. And you can see that, you know, there's a reference frequency, a level, unit, duration, and actually you can calculate THD out of the calibrator using the calibrator and specifying harmonics here. And also the function will return an FFT, an autopower spectrum analysis using a flat top window, right? So we could certainly use those features, THD and autopower spectrum, but in my case, I just want to start the calibration, get the sensitivity, and make a very simple pass-fail on the sensitivity. All right, I'm back to the button 1 underscore click, and I just have to add this called button 3 underscore click. So I want to push the command send command button when I'm done with those 2 lines. Okay, so I think we're ready for a quick demo here. So I'm going to execute the app. I'm going to place my microphone on the calibrator, turn on the calibrator, and click CalMic 1. You can see the clock is running. And at the end of the 5 seconds, I'll get the sensitivity from the microphone. And I'll have also a THD estimate of the calibrator. This is looking good. So what I want here is to grab that number and put a label pass or fail with a color, green or red, based on the sensitivity I get here. And this is where the my exit event is going to be very useful. So if I go back to my code page here and I search for my exit, here we go. I want to make some condition, and I'm going to do that with a select case. So, and I'm going to select case based on the text box 1. So when the text box 1 equals to calibrate input channel 1, like here, I want to read the input channel XML and get the sensitivity. So those are predefined functions I already defined there, but this one will read the XML file that relates to the input channel and will collect the sensitivity automatically. I'm going to manage the colors such a way that when the label 1 will display pass. That means the sensitivity will be lower than 65 millivolt per Pascal or above 40 millivolt per Pascal. If it's not the case, the label will show fail and the color will be red. Okay, so I just need to do select here and select. Okay, so let's try that real quick. I'm still calibrating the microphone. The calibrator is on, so I'm going to click cal here. And after the 5 seconds, you know, I'll have a pass here, which is a good sign. So the sensitivity is equals to 53 millivolt per Pascal, and the label reference that and will tell me that the microphone is healthy. Last but not least, I need to work on this FRF plus THD and I'll be done here. So that button 2 will use this function that I already prepared called write input channel for step sign. So this is a function that is going to force to have certain XML field. So I want to activate, you know, set the activation to true for the input 1. I want to work with a reference channel, and in my case it's going to be generator 1. So if you want an FRF, you need a reference, obviously, and this is how we pass that reference to the XML and to the engine. And I'm going to use millivolt per Pascal as a unit, and I'm going to turn off all the other channels, because if I don't do that, if I turn them on, the frequency response will be calculated on all active channels. So this is kind of important to turn that off. And then finally I will write the XML, you know, and save all the parameters. The next step is going to be able to call, we're going to call another function called write output channel for step sign. This is going to force the output generator to be active, and then finally there's another function called write step sign text XML, and that function specify the type of analysis we want to do. So it's going to be an FRF, but it could have been an auto power spectrum, or it could have been a phase assigned spectrum. There's different choices here, and it will also specify the name of the DUT, the device under test you have. And then at the end, I want to make sure that the text one of the user interface will reference that step sign test. And I'm going to call the button 3 that will trigger the command here. All right, so I think we're good. And the last thing, the real last thing I need to do here is to handle the my exit and make sure that when the process is done, I can read the data. So it's going to be a new case here. It's going to be select step sign test. I'm going to search for the last file that has been created on the drive in a specific location, and the function will return my file. And I have a function called XML import mixed results. So the XML that is generated by the engine here will contains autobar spectrum, complex FRF, so real part, imaginary part, THD, rub and buzz if you ask for rub and buzz. And so we'll have everything in one file, one XML file, which will be very easy to read. So this is convenient because if your test is a given speaker, given headphone, every data will be grouped under one file only. Okay. All right, so that function will return a table called my amplitudes that will have all the amplitude data associated with the results, right? So I'm going to create a couple variables here that will help me to do the pass-fail. And I'm going to read the node 2 of the XML file, and I'm going to transform that into dB values, right? So here's my node 2 coming out of the amplitude table. I'm taking the log, and I'm looking at if my dB value is above 35 or below minus 15 dB. It's the case, FRF will get false, okay? If the FRF gets true, as a default, that's the default state here, I'm going to have a FRF passes and the label 2 will be green. If it fails, I'll plot FRF fails, and the color will be red. Okay, and we'll do the same with the distortion. But the distortion data in my case here, it's going to be located at the node 15. Okay, so it's going to be the same node every time I'm doing my testing. Okay, so this is going to be very convenient, and I'm going to turn the color green or red depending if the THD is above 3% or below 3%. All right, let's test the code now. I'm going to execute the app, so I'm going to calibrate the mic again. Done, and it's passing. I'm going to put the mic on the speaker and click FRF plus THD. And the FRF passes and the THD pass. So we're good. I hope you got inspired by this presentation. And if you want to receive a demo pre-release kit, feel free to contact your local HBK sales engineer. The kit will come with the 3670, the pre-release EA engine with the demo license. Additionally, if you're interested, HBK has a global engineering software service group located in the States and also worldwide. This group is capable of developing and deploying apps for doing quality control for your production lines, or tackle sophisticated R&D application if you wanted to. I've been using the EA engine for several months now, and I must say it saved me a lot of time. My job was to interface what I wanted to see and wanted to do and nothing else. This was very comfortable and rewarding. It's the Q&A session now, so feel free to ask me all the questions you want in the next few minutes. Thank you, everyone.